Hello, everyone. Welcome to another episode of Cuda Education. So, today I want to do a deep dive into the files that were added to our project. I promised that I would do. This is going to be Clean Slate 1.621. So, it's Clean Slate 1.621. And the reason I have it numbered that way is because 6.2 dealt with adding the files just on a surface level, and then 6.2.1 is going to be just the details of 6.2. So 1.62 was just surface level, what's going on with the files. What files were added. 1.621 is going to be a deep dive into those files. I promised I would do it, and I guess it's just time for me to get it done so we can move on. All right. We added some files to our project, and of course, right now we're at the stage where we're generating a triangle, right? An odd triangle, but a triangle nonetheless. And we're trying to get to our modern renderer, full application where we see the bistro and all that stuff. Okay. So yeah, let's just get into it, guys. So we have AAPL simple.metal. Now this is a shader, which means it's a program that runs on the GPU. I'm running on Apple Silicon. So on the Apple GPU that's attached to the, that's you have the CPU and the GPU. So this is the Apple GPU. .metal means that it's a shader, it's running on the GPU, it's a GPU program, all that good stuff. So this is the first file that runs on the GPU rather than the CPU. It contains two tiny programs called shaders that the GPU executes for every vertex and every pixel. So every vertex and every pixel, which is basically everything that makes us see this triangle here. This is the background and this is the pixel for our generated triangle. Okay. These are pixels also, but it's the background, which is a different process. This is what's generated from the GPU, right? And our metal application and all that, right here, the triangle. Okay. It contains two tiny programs called shaders that the GPU executes for every vertex and every pixel. So we include the metal standard library here and the SIMD, single instruction, multiple data. I covered that in a previous video. Basically you execute one thing and you do multiple operations with that one thing. So like matrix addition, multiplication, all that stuff, right? Multiple rows, but it's one instruction. And then import APL shader types.h. Okay. The imports metal underscore std lib standard lib gives us GPU side functions, right? simd.h gives us vector matrix types. So right, so just like what I said, APL shader types.h is the shared header we created in step 2. This is why it exists. It defines buffer index constants, APL buffer index camera params, etc., that both CPU code and GPU code reference, guaranteeing that they agree on which buffer slot is which. Okay. Notice that it's a header file, guys. So shader APL shader types.h is a header file. So you guys know that header files can be included in both CPU side code and GPU side code. It's a header file. It's an include. It's an import, right? Notice that you even have, for this guy, you have import. You do have include here for this .h, but we'll just we'll look at that at a different day. But this is a header file, so it can be included on CPU side and GPU side. So with this thing, the reason that we have this on both CPU and GPU is because we have to make sure that the buffer slots, basically the containers that we store stuff, the kind of like your locker room, or if you have like any kind of storage container system or whatever, you want to make sure that what the CPU, where the CPU thinks something's stored and where the GPU thinks something's stored is the same place. Okay, you don't want divergence with that because that's just confusing. All right, so that's what that is. And then we have our strut APL simple vertex out, and that gives us a position, right? Same thing here. Okay, the output of the vertex shader. The position attribute tells Metal this is the clip space position. Use it for rasterization. Okay, Metal takes this 4D coordinate and figures out which pixels the triangle covers. We'll leave that alone for right now. We have our APL vertex, simple vertex out, simple vertex, simple shader. And we have some parameters along with it, and then we do some processing. Okay, so so we have this guy, and we have vertex simple shader. Now this and this somehow, because we have this guy here and we have this guy here, but we have this as a function. Now notice that this takes 1, right? 1, 2, 3 parameters. Okay, and then we do some processing with the information given. So APL simple vertex out, and then out dot position. See, because this is the strut for out dot position is WVP matrix times float for position VID, and then we add this extra parameter because it wants, and then we return the out because it wants a 4D thing. The vertex shader runs once per vertex 3 times for our triangle. It receives WVP matrix, the camera's view projection matrix, bound at buffer slot 1, APL buffer index camera params. The constant and means it's a single matrix shared across all vertices. All right. Positions. Positions. A pointer to an array of 3D positions bound at buffer slot 3, APL buffer index vertex mesh positions. The device address space means it lives in GPU accessible memory. Okay, so constant device. The device address space means it lives in GPU accessible memory. And then VID, the built-in vertex ID 0, 1, 2, Metal provides this automatically. So Metal provides this automatically. All right, so that's that. So these are the 3 parameters that we put into vertex simple shader. And then what happens is that the one line of actual work, WVP matrix times float for positions VID, which is 3 items, float 3, and then we add the 4th 1.OF, right? That gives us our position. The one line of actual work, WVP matrix times float for positions VID, and then the additional 1, which gives us a 4 dimensions, right? Promotes it to a float for by adding the W equals 1.0. Because 4x4 matrix math needs 4 components. By multiplying and multiplies by the view projection matrix, right? So we have our 4x4 here, and then we multiply with the view projection matrix, right? WVP. Okay. See, notice that this is 4x4, this WVP matrix. Okay. And multiplies by This transforms from where is this point in the 3D world to where should it appear on screen, clip space. All right, so that's all that's happening here. We have fragment. So we have fragment, simple shader, constant. We have a parameter, constant float 4 and color buffer, AAPL buffer index fragment material, right? So that's a parameter of the thing, and then it just returns a color. So what's this all about? So the fragment shader runs once per pixel that the triangle covers, right? So basically everywhere you see this color here, runs once per pixel that the triangle covers. It receives a single color from buffer slot 3, APL buffer index fragment material, and returns it. Every pixel gets the same color. No lighting, no textures, no shading, just flat orange. We'll make this much more sophisticated in steps 5 and 6. Yeah. Guys, one thing that I'm not gonna cover in this episode, but I mean I do want to investigate, is where these slots are decided. I don't remember if in previous episodes we actually declared where the slots are, but it's a topic of investigation that I want to dive into at some point. So I will get into that at some point. I'm not sure how these slots are decided, or if I can tinker with where the slots are or mismatch the slots to see what happens or what have you. But I digress for now, but I know it's something that might be confusing because I'm not sure where the slots are or how it was decided. All right, so we do APL renderer now, .h. So let's go there, APL renderer.h. We're doing the header file, so .h. Right, header for the renderer class, which performs metal setup and per frame rendering. So import metalkit.h, interface APL renderer ns object mtk view delegate, init with metalkit view. Okay. So deliberately minimal. The renderer conforms to MTK view delegate, taking that role from the view controller. We have discussed this. We move the view controller, we move the delegate from the view controller to this guy here. So taking the role from the view controller, and has a single init method, init with metalkit view, and has a single init method that receives the configured MTK view. Right, so it receives the configured MTK view. Everything else is private. The header reveals nothing about pipeline states, buffers, cameras, or shaders. The outside world just creates it and sets it as the view's delegate. Okay? Right, so that's that. Let us go to APL, the renderer, okay? Okay, so the implementation. Implementation of the renderer class, which performs metal setup and per frame rendering. So we import APL renderer.h, APL camera.h, and APL shader types. Okay, so we have our variables, right? Instance variables. This is where all the work happens. Let's walk through it section by section. So we have all of our variables, which are also here, right? 7 objects the renderer holds for its lifetime. Device, the GPU, grabbed from the view, same as step 1. Command queue, moved here from the view controller. So again, guys, we're moving stuff away from the view controller into the renderer, just to keep things clean. Remember, the view controller is more of a UI, user interface thing. It's not really supposed to be doing rendering logic and all that. All right, simple pipeline state. So simple pipeline state, a compiled immutable object that tells the GPU, use this vertex shader and this fragment shader with these pixel formats. You create it once at startup and reuse it every frame. So that is our simple pipeline state. Then we have our depth stencil state, right? This guy right here. Tells the GPU how to do depth testing. Closer objects occlude farther ones. Even with just one triangle, we set this up because it matches the reference project's pattern. Remember, guys, our project is much more advanced than just a triangle. So we kind of need to just, set up the framework for how things supposed to go. And, we could add in, so that later on we could add in the complexity and the depth testing and all the grand things that we want to do. But we actually have to at least put a placeholder here for now, just so we're good going forward. All right. Then we have our vertex buffer, GPU accessible memory holding for our 3 triangle positions. Color buffer, GPU accessible memory holding, 1 RGBA color. Then we have our camera, the APL camera from step 2 finally being used. All right, so that's that. Init with metal kit view. Okay, one-time setup. So init with metal kit view, one-time setup. So device, let's do that right here. So we have our device, view.device, command queue, device, new command queue. The renderer configures the view's pixel formats, right? BGRA 8 unorm underscore sRGB means each pixel is 4 bytes, blue, green, red, alpha, in sRGB color space. The depth format, depth 32, float, tells MTKView to create a 32-bit floating point depth buffer alongside the color buffer. Okay. Then it calls the 2 setup methods and creates the camera. So, self, then it creates a 2 setup method and creates a camera. So load shaders and create the render pipeline state. So self, load metal with view, and then self, load assets, create triangle geometry. All right. This is the first time APL camera gets used. Init default perspective. So down here. So that's this guy right here, right? We have this, and then we have our aspect ratio, width divided by height. Return self. This is init with metal kit view. So we have our view. So this is all contained in the init with metal kit view. So this is the first time APL camera gets used. Default perspective puts the camera at position 14.04, right, okay? This is the first time APL camera gets used. Looking towards this. Now, I'm not sure where these dimensions are coming from, all of that, whatever. The same default as the reference project's bistro scene viewpoint. We set the aspect ratio from the current window size, right? So width of the window size to height of the window size, and that's the aspect ratio. You divide width by height. Load metal with view. Compile shaders, build pipeline. Default library, vertex function, fragment function, right? So vertex simple shader, fragment simple shader. Okay. Xcode compiles all .metal files into a single default library at build time. So this is it right here. Xcode compiles all .metal files into a single default library at build time. We look up our 2 shader functions by name. So the vertex function and the fragment function, right? We look up our two shader functions by name. These are the same names we used in AAPL simple.metal. So you guys remember these were the names that we used, right? All right, AAPL, create the render pipeline state. So this was load the shader functions from the default library, and now we create the pipeline state, right? So that's the same as here, all of this stuff right here, all right? Create the render pipeline state. So MTL render pipeline descriptor, this, all of this stuff. We have our label, simple pipeline state, vertex function is vertex function, fragment function is this, which is these guys right here. Color attachment is color. The pixel format is a pixel format. Depth attachment is a depth stencil format. So a pipeline state descriptor says, I want to render using this vertex shader, this fragment shader, outputting to this pixel format with this depth format. The new renderer pipeline state with descriptor, new renderer pipeline state with descriptor, call, compiles and optimizes this combination into a GPU ready object. All right. So I guess that's this guy right here, GPU ready object. The new renderer pipeline state with descriptor, call, compiles and optimizes this combination into a GPU ready object. This is expensive. It compiles GPU machine code, so you do it once at init, not per frame. Right? So you do it once at init, not per frame. This new renderer pipeline state with descriptor call compiles and optimizes this combination into a GPU ready object. This is expensive. It compiles GPU machine code, so do it once at init, not per frame. All right. Let us continue. So MTL depth stencil descriptor. So now we're down here. Oh, and then notice that if it failed to create simple pipeline state. So if there's an error in this step, we get this notification. Failed to create pipeline state. All right. So create the depth stencil state. All right. So MTL depth stencil descriptor, depth stencil, depth enable right, depth stencil state. All of this stuff right here. Right. Depth, right? So depth, and we played around with this stuff in a previous episode a while back when we actually were working with the bistro, right? So the depth stencil state MTL compare function less means only draw this pixel if it's closer than what's already there. Depth right enabled equals yes means update the depth buffer when we draw. With just one triangle, this doesn't matter much, but it will be essential when we have overlapping geometry. So obviously for this application right now, we do not have overlapping geometry, but we will once we get to the bistro. Okay. Load assets. Okay, so create the triangle. All right, so create the triangle. So we're this triangle vertices, all of that stuff. 3D points in world space placed in a couple of units in front of the default camera. New buffer with bytes. Copies them into a metal buffer. GPU accessible memory. Storage mode shared, which is this guy right here, means both CPU and GPU can see this memory. Fine for small static data like this. Okay, so we have that right there, and then we have our color information. So we have float for color, and then we have a similar setup here. A single RGBA color, orange, in another buffer. The fragment shader will read this for every pixel. Okay, and then we have Drawing MTK view per frame render loop. Didn't cover this, but okay. Aspect ratio, we know what drawable size will change. If you change the size of the window, so if you go from full screen to a little small window, you're gonna have to recalculate the aspect ratio for the camera, all that good stuff, right? So per frame render loop. So this is gonna be our per frame render loop right here. Okay. So camera update state, float view projection matrix, right? So first update the camera's matrices. This is where the dirty flag pattern from step 2 pays off. If nothing changed, update state is nearly free. Then grab the combined view projection matrix. So this has to do with, like, I guess if something happens with the camera, you have to update it, okay? If nothing changed, update state is nearly free, right? MTL render pass descriptor. Get render pass descriptor, and then create command buffer and render encoder. And I guess this is where we start the render encoding, right? Same pattern as step 1, get the render pass, which triggers the clear, create a command buffer and encoder. But now we actually encode drawing commands before ending, right? So now we're actually doing stuff with the encoder, like I mentioned before. Right, encoder set and set depth stencil, right? Tell the GPU which shaders to use and how to do depth testing. Tell the GPU which shaders to use and do the depth testing. So set vertex buffer, set vertex bytes, set fragment buffer, set vertex buffer, set vertex bytes, set fragment buffer. All right, so set the vertex buffer positions, offset 0, at this, that, the other, and then we do the bytes, size of whatever, and then we do set fragment color, all of that stuff. Right, so tell the GPU which shaders to use and how to do depth testing. All right. Bind data to buffer slots. These at index, right? At index. These at index values match the buffer attributes in the shader. Okay? Match the buffer attributes in the shader. Buffer and attributes in the shader. Slot APL buffer index camera params. Right? 1. The vertex shader reads this as view projection matrix, W view projection matrix. Slot APL buffer index vertex mesh positions 3. Right? This guy right here. The vertex shader reads this as positions. And slot APL buffer index fragment material 3. Fragment shaders read this as color. Right? Set vertex bytes is used for the matrix instead of a buffer. Set vertex bytes. Note set vertex bytes is used for the matrix instead of a buffer. This is a convenience for small data. Metal copies it inline into the command buffer. No need to create a separate MTL buffer object. We'll leave this discussion alone for now, but okay. Encoder draw primitives. So we have encoder draw primitives, MTL primitive type triangle. So the draw call, draw one triangle using vertices 0, 1, 2. The GPU runs the vertex shader 3 times, once per vertex, rasterizes the resulting triangle, then runs the fragment shader for every pixel inside of it. Then runs the fragment shader for every pixel inside of it. Yeah, okay. Uh, Encoder end encoding. Command buffer present viewable present drawable dot view dot current drawable commit. Same ending as step 1, finalize present submit to GPU. Okay. Right, so let's just go right here. So the data flow. So we have um, APL renderer, APL simple metal, simple.metal. So view projection, camera view projection matrix, buffer 1, WVP matrix. Vertex buffer 3 floats, buffer 3 positions, VID. So vertex simple shader position equals matrix times vertex, rasterizer, which pixels inside, buffer thing, whatever, whatever. Color buffer 1, float 4, buffer 3, color, fragment shader, return color, and then we get our screen. Yeah, return color, and then we go to screen, basically. This is screen. But anyway, guys, that is it for this segment of the discussion, right? So I wanted to just give a little bit more detailed run of the 3 new files added. We have a much better understanding of what's going on. We will move on to the next section in the next video. But thank you for watching Cuda Education. You know what to do to help the channel. Encourage anyone that has a Mac, all that good stuff, to consider learning this stuff with you. Another thing I want to mention is that the bistro scene that we're working towards. It was my understanding that only Apple Silicon Macs could run the application. Apparently, from what I'm hearing, at least what AI is telling me, is that perhaps it could run on Intel Macs. That's what I'm understanding. It could run on Intel Macs. It's just that some features are disabled. I don't know. I can't vouch for it. I initially mentioned that the bistro scene was a modern renderer. So for you guys that are new, modern renderer, the Apple Metal sample code library, modern renderer. If you look it up on Google, um, I initially said that that application was something that could only run on Apple Silicon, so M series Macs, right, with the M chip. But apparently, maybe it could run on Intel Macs. I don't have an Intel Mac, so I can't vouch for whether that's true or not. Okay, but this does take advantage of the latest features of Metal. I do know, what we're seeing and how this application runs. It's assuming Metal 4. But as far as the Intel Macs, I don't know. So if you have an Intel Mac, you kind of have to just, maybe try and run it yourself and see if it works or not. Or maybe it will work, but some features will be disabled. I don't know. But anyway, guys, we are moving ahead. I think we have one more step, and then where we're still seeing the triangle here. But then we will hopefully start to see more of the bistro scene where we're actually loading assets and things are really starting to change, which is what I'm excited about, which is what I kind of want to get to, but we have to do it, in an organized fashion. So we'll take our time and get there. But I think it's just one other episode, and then we start. After that episode, then we start loading assets and seeing stuff change in a real way, and it's not just a triangle. Anyway, guys, thank you for watching. Have a great day.